Okay, first of all, again, my apologies for this. It was difficult to drive, so um, I did it online. One of the advantages of technology. Now, one request I have, I think I finally did it in a way that the appointments actually show for everyone. I would appreciate it to go over the uh, appointment, right? Click over there, accept series, or click on it, RSVB, response to series, and click on accept. Like that, you're gonna be um, set for the appointments, and I'm gonna know that I can actually uh, know how many people actually saw the thing, and if like 15 people are missing, I just want to make sure that they got the message. So please do that. Let me take this virtual machine away. The next thing is the workshop. So not to get confused with workshop 0 for IPC 1 for OP244 in our uh, in our notes. I actually added workshop 0 over there. So courses, and finally I sent the welcome message. So probably you saw the welcome message as like the fifth message. Over here is welcome, yada yada yada. So if you actually go to that welcome thingy, workshop 0 is there. So if you click on it, it takes you actually to the workshop 0 that I put it in our repository. Um, I will remove the final, or maybe I can actually leave it over there. I'm going to set it in a way that you can actually submit this. It's a good idea to keep track of uh, your information tied to your name, because when you submit, it's a silly thing that you have to submit. You just print 5 lines and you send it to me. So I'm going to open the submission over here. Forget about reflection. You don't need no reflection. I will probably remove that one. I'll take the reflection out. All I need is the workshop 0 submission. That I'm going to set it, and you have it till next Friday to do it. And for section E, it's going to be next Wednesday or something. If you have any questions, please activate your microphone and talk, so I don't miss what you're saying. And that's that. So all the little things that we need to know about the subject is here. The addendum is going to be hopefully up by Monday when I uh, do the modification and pass it through. What is the and that's it. So please go through the steps of this one. Anything that I think I'm almost positive that half of these things you've already done, like putty installations. I don't think anybody has it, like Git and stuff, GitHub. These things, please go through them and make sure that the GitHub account that you're creating is your own and not in Seneca organization. Um, any questions down to this point? If you have any questions, don't forget the raise hand thingy, so you can actually click over here for raise hand. And to kind of give me hope so I can see you're actually uh, listening to me every now and then when I say any questions or do we understand, give me a reaction like that so I know that you're actually there. I'm not talking to myself. Let's put this thing away. All right. And that's that. Oh, thank you, Ruda. Okay. Now I'm going to kind of fill in the blanks and go through the stuff that we had throughout in these three things that we are supposed to do for week one, um, and kind of fill in the blanks and um, that's going to be it. Hopefully, it's going to be a short session. I don't know how long it's going to take, but we'll see. And if anybody has any problem with setting up their computer, afterwards, I can stay and help you. So let me know if you need help. Oh, and also for Mac, those people who have Apple, um, you go to the Apple instructions. I just want to quickly mention that anything that you are doing on your computer, the terminal of Apple, it's the exact same thing on Matrix. The only difference is that you need to identify if your um, shell is ZSH or it's bash. If it's ZSH, you need to change the dot profile on Apple to Z profile, and that's it. Other than that, everything else is identical to Matrix, which makes your life easier. Your setup is much shorter than the setup for Windows. All right, now back to this part. The very first thing I'm going to do is to pull the repository for this semester. And that's exactly what you need to do every time that you're working on your stuff. This is updated. That's nice. Now I'm going to create um, the project for today's session. Empty project C++ Windows console. Select it in the repository that you're working in. So you're 345. Make sure you are creating it in the repository that you're in. So we got to be B May 9th. Create a file. Set the properties to be C++20. Apply OK. And write the main and we'll start. Okay. 345NDD, OOP345NDD, and May 9th. Okay. Also, one request, can somebody type something in a chat? I just want to make sure that the window that I'm creating over it, I opened, actually works and I can see your chats when you're typing. Got it. Perfect. Thank you. So everything's good. Done. All right. So where were we? So I'm going to quickly go from the beginning, and any part in space that you have any question, activate your microphone and uh, tell me what's going on, because this is the first week. I'm not very picky about you not having your microphone with you, but at any other time that we are going to actually be in class online, you must have a headset, and if you don't have it, go get it as soon as possible. You must have a headset, and you need to be able to talk to me uh, when I ask you a question. So, encapsulation, inheritance, polymorphism. Uh, any problem over there? Building blocks, values, objects, variables, references, functions, types, class, templates, namespaces. Um, any problem about this one? You have a chance to later on again. So after we're done today, you're going to study these three things and you're going to come the next day with questions. So I expect to get questions that we need to ask. So type categories, fundamental types are the types that are built into the system. Building types are the one that we are creating from fundamental types. They're essentially derivatives of fundamental types, like if a fundamental type is an integer pointer is a built-in type, um, or integer reference is a built-in type. User defines, we have two types, concrete and abstract. Built user defined types are types that are made out of the other types, like fundamentals and built-ins, like a structure or an array. And an abstract user defined type essentially are we learned from OOP244. These are classes with pure virtual functions, classes that are not complete. Definition of certain functions are unknown. Are we okay down to this point? I don't see a single thumb up over here. There you go, 1%. Good. 2, 3, good. Yeah, and I see many people by mistake raise hand. Raising hand is for question. Yeah, there you go. There you go. Perfect. All right. Um, so, scope. Talking about scope. Local, class, namespace, global. We've talked about these things. Local scope is essentially uh, all the scopes that you have within curly brackets. Class scopes are scopes that are accessible by inner scope via class membership, like methods and stuff like that. Namespace scope is the scope in which the names will collide if they have the same name. So you essentially create a block and you identify you set up the names that are relative to the namespace so they are not repeated. And global scope is a scope that is visible to everyone. Um, Namespace is a little bit more complicated than that. We're going to go through it. Global scope and stuff, we know it. Linkage, you've already dealt with it. Essentially, a global scope is not really global. It's a file scope with an external linkage. We make it global. We make a file scope variable global. Talked about compilers. Code segment, data segment, and stack segment. So code segment is essentially contains um, all the compiled machine instructions, the programs and executable stuff that you have. That's code segment, and it's read only. Nobody can touch it. At any moment that you write anything on code segment, you get a segmentation fault on Linux. Essentially, you're going out of your segment. Data segment stores the global and static variables with predefined and non-zero values. Okay, so essentially, yeah, that's exactly what it is. So when you put static variables and global variables, um, and you put some values in them, those are global variables. It's divided into two parts, initialized and uninitialized variables, um, which we're going to come up to. Um, the stack segment is essentially used for local variables like function parameters or function call management and things like that. And it grows and shrinks with function calls. So as you make function calls, your stack grows bigger and bigger. The more nested functions you have, the stack grows more. So let's say in function A you call function B, in function B you call function C, in function C you call function D. Your stack grows fourfold. The least amount of function calls make the stack smaller. Now, if by mistake you call a function in itself, so function calls itself, if it's based on a logic, it's called recursion, which we're going to learn later. But if you do it by mistake, it's going to create an internal loop, which essentially a function calls itself, and the stack keeps growing, and the program terminates and crashes with a stack overflow error. So whenever you see a stack overflow error, it means by mistake you call the function in itself. Heap segment is used for dynamically allocated memory that we use it that we kind of use new for it. So let me just go over here. Where's the things? Here it is. So essentially, if I create gvset10, this is a global variable. Okay, I know it's not really global in the manner of scope because it's file scope, but through extern you can make it global. So this goes to data segment. Because these are initialized. Okay. And then after this, you have things like int uh, GVU. So this is a non-initialized global variable, which goes to BSS segment, they call it. And there is a reason that the two segments are different. I'll explain later. Um, and then we have our say function, and inside our function we can have the local variable. This is in stack, so this is in stack. Uh, and the reason that the stack keeps growing, because when you call the function 5 times, 5 versions of local variables going to get created, and therefore it's pushed into the stack as it grows forward. And then we have the heap. Something like that. So this is in heap. Okay. And obviously we're going to delete heap variable at the end. And if you want to know what is where, first of all, we're going to learn this later on. But anybody remember that when you're creating an array, where does the um, what should we call it? The address of array, where the an address of an array is kept. Anybody remembers that? You can answer in the chat. So if I have something like, if I have integer a20, we know that these are, it's in the chat. No, don't tell me where in category, as like when I write int a20, and if you want to print the address of the beginning of the array, where is it held? I'm waiting. First element of the array, not on the heap again. First element of the array, of obviously it has the address of the beginning, but how do you extract it? Should I call somebody? Everybody's quiet. Okay. Hawk, thank you very much. That was a beautiful thing. Okay, Anton, thank you. Anton actually gave the correct answer, which is equal to what Hawk said. But the thing is that we need to know and remember that uh, address of an array is kept inside uh, the name of the array. So essentially, from what you see in the text, address of A0 is the exact same thing as address of A. Let me demonstrate. So if I say over here integer A50, and if I say cout reinterpret cast of unsigned long, and I put address of A0, and I do the exact same thing and I put only A, the result will be the same. Do we understand this? You know what? Actually, uh, please reply in the text because over here I don't see the thumbs ups or thumbs up coming. I want to see yes or no from the thing. So if you have any problem, let me know. But it's a good idea to reply in the text something like yes, so I know that we understand what happens. Okay, that I don't like about Teams, and I hope one day we're gonna get the big blue button back. Anyways, so only 1% said yes. It means out of 27 people in class, only now two. All right. Yeah, bombard me with yeses or no or something. So I know at least so something. Okay, good, 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 good. Okay, all right. Okay, so that's that. So now we know. So now we know that the address of the beginning of the array is within the array. Now, what I want you to do is to understand that functions do the same thing too. So the name of the function actually holds the address of the beginning of the function. So if I do this reinterpret cast of mine over here, I can do this. Let me see. I've written this like that over here, and I'm going to have reinterpret cast like this. So like this, you can actually see exactly where are those memories are. So I forgot to call the function. My apologies. So now in here, I'm gonna say foo, and I run it, and this is what you see. So this is the code segment where the code segment is. This is where global variables are. This is where global uninitialized variables are. This is the address. So just take a look. Just look at the size of the address of the stack and address of, so you see how much different there are, and heap variable and so on and so forth. Okay, so that's that. So now we know. It's just an explanation to see where all the code segments are. So I'm going to call this one a code segments. So we know. Now we can continue. Questions down to this point? All right. One person said, no, I'm happy. Okay. So let's continue with the rest of the stuff. Where is that? There we go. So, oh, that's it. So go to the next one. C++ is building blocks. Declaration, we talked about it. Declaration was essentially introduction of entities in a program. So essentially, every single thing that you want the program to recognize, those are your declarations. Definitions are essentially they give meaning to every single thing that you have. Like you can create class foo semicolon. That means you have a class. That's a declaration of it. But when you actually say class foo and you put information in it, that becomes its definition. Um, and yeah, and then you can implement the class in a CPP file and so on and so forth. So that's how it works. Block scope, we know what it is. Anything inside a curly bracket is in a block scope. Class scope, we talked about it. Well, it's redundant actually. Global scope, shadowing. Shadowing is important. Any inner scope that has the same name entity of the outer scope will shadow it. It doesn't have to be the same type. I can have integer I over here and double I over here. This double I will shadow the integer I. Same name, it will shadow it. You gotta know that shadowing happens. External linkage, as we mentioned, when you actually say extern int, something like that, you are as if you are putting a prototype for a variable. Extern int share me does not create an integer, it's a declaration for it. Then inside one of the CPP files, not two, only one of the translation units, only one of the translation units, you're going to put int share me. And then this extern could be in everything else. Therefore, they can actually share this variable from file to file, from translation unit to translation unit. And it's exactly like a function. You create one function in one CPP file, you spread its prototype wherever you want to use it. Whichever file have access to the prototype of a function can call it. So prototype for code segment is extern for variables. Do we understand this? Anyone? All right. As I said, I'm gonna create a program that randomly is gonna show the name of a person on the screen, and that's gonna be the person who's gonna answer that the next time. So I can actually keep track of who is really participating. We're gonna bring that up soon. Hopefully, the next session you're coming in, it's gonna be on my computer. All right. All right. Next. Uh, Internal linkage, when we call we call it static, but static essentially makes the variables uh, it makes a variable's lifetime global, but the scope limited. Now you can have two different types of static. You can have a static variable over here, which is absolutely no use. This is completely wrong. To have a static global variable, it doesn't make sense because it is static already. It actually falls to the category of static. A static variable is the variable that keeps its value. So writing static outside of a function is for no reason. The only reason you might want to use static is when you do the static inside a function. So when the static actually happens inside a function, it keeps its value and it will never die. Uh, the CV qualifiers. When you do not put any type of qualifier for a variable, that variable becomes automatic, which means its lifetime ends at the end of its scope. That what we call uh, uh, an automatic variable. A constant variable is essentially cannot be modified after its initialization. Anything you want to do after will uh, it prevents its modification. A volatile tells the compiler not to optimize read writes. So the value may change unexpectedly if hardware changes the same place that the variable is doing. So volatile essentially, when it's, let me tell you what non-optimization means. Um, let's say I have a prisoner inside a prison cell. I check the prisoner in the morning, I look at the cell and I see the prisoner is in the cell in the morning. Then at night, and I know that the door is closed, it's not going to be open all the way to the night. When at night somebody asks me if the prisoner is in there, I'm going to say yes. Why? Because I know the door is closed and the prisoner cannot go out. This essentially means that the prisoner's location is not volatile. It means I can optimize my reading. Whenever you tell me if the prisoner is there, I'm going to say yes, because I checked in the morning and I have the key and no one else can go in there. You ask me, it's optimized. I can know that it's in there. Okay? So that's that. That's non-volatile. The other one is if somebody's in a washroom. If you come and check the washroom and you come back and it says, is somebody in the washroom? You can say, I don't know. When I was there, nobody was there. But now that I'm here, maybe the person is someone else is in here, or if somebody was there, it's out. Why? Because it is being changed without my knowledge. Therefore, if you really want to know if somebody is in a washroom or not, I need to have a volatile access to it. It means no optimization. If you tell me if somebody's over there, I have to actually go and check the washroom. That's when you are in your programming. Sometimes memory locations are accessed not only by your programmer but other things. If that's the case, for you to be sure the value that you have over here actually has the value that you think it has, you should consider it to be volatile. Therefore, anytime you ask for it, the compiler will go there and check it, and it will not optimize the value. Do we understand this? Hopefully we do. Okay. All right. So when you have a volatile variable inside your program, you can change it. It means when you look at the washroom, you can actually go inside the washroom yourself and occupy the washroom. That's when you have a volatile variable. A constant volatile variable, it means you can check to see if the washroom is full or not, but you're not allowed to go in. That's all. But still, other people can come and go. With a constant volatile, you can't change it, but others can do. What are the uses in our OOP345? I've never seen it being used, but who knows? Maybe we'd use it sometime. Okay, typedefs are creating new types uh, out of the old ones. So uh, give me a second. So typedef uh, is to create a type out of any other type that you have. It's as simple as it can get. I cannot, uh, and it has side effects that you can use for many different things. Uh, let's say if I want to have something like this, unsigned long integer pointer. Okay, unsigned long integer pointer foo, and I want to receive an unsigned. You see, it's 3 hours I have to type this thing. I don't like it. So what I can do over here, instead of keep typing it over and over, I can actually say typedef. As simple as that, typedef, and say unsigned long. I can go ULLIPTR. So instead of typing that long thing, I can simply say ULLIPTR foo and ULLIPTR X. So what happens over here, this returns an unsigned long integer pointer and receives an unsigned long integer. And this X is actually a pointer too, just be aware. So that's one of the benefits. You can actually shorten long type names that is difficult to take care of. Okay. Another thing that you can do with it is another thing that we used a long time ago in the galaxy far in C language. If you recall, in C language, if you wrote in C language, if you wrote struct, let's say employee and whatever over here, if you wanted to instantiate it, you had to mention struct employee employee something like that. So what they did, they said, hey, uh, in C language, we used to do this because we didn't want to keep typing struct. We did what C++ does. C++, when you create a struct employee becomes a type. You don't need to rewrite everything. You just write this. So what we did in C language, we took this employee thingy out from here and we wrote over here typedef and we put the employee over here. So what it did was that say I am creating a type that its name is employee. Therefore, in C language, you didn't need to write typedef before and after. So that's what it is. Uh, any questions on typedefs? All right. All right. Namespaces, you know exactly what they are. I'm not going to fry your brain with this. I'm just going to tell you the new stuff about it that you didn't know. Okay. First of all, namespaces. You know exactly what they are. We've done it in OOP345. What you need to know about namespaces is that the using that you are using for a namespace can only be used not only for the namespace name itself, but also members of a namespace. So if I say using namespace, it was somewhere over here somewhere. So I have a namespace over here, dot, that has a leader, and I have a hat that has a leader. So these two, they both have a leader function the same way. If I actually write over here, if I want to access the dot leader, I'm going to say dot leader. So this is perfectly good. Okay. Now, if I want that leader thingy to only be used, I can actually use the function in there. So I can say using dot leader. And you can use this not only with namespaces, with classes and things like that too, if you don't want to reuse the name. But anyways, this means if I mentioned leader, I mean the one that is with dot. Obviously, if you cannot put both of them, that's crazy. If you wanted to use only if you want to use anything else, as you had to qualify it. But by doing like this using only uses leader in the code. If you say using dot, the entire thing comes that you have done it in OOP345. Are we okay with this? Show me a thumb up. Okay, thank you. Yeah, so they call one of these declaration. So the using that only aims to make one member of a namespace to be used is called declaration. Using directive is the one that brings the whole thing in. So you're going to say using namespace something. In here, you are not saying namespace, you're just putting the name. But when you're using a directive, it brings everything in. Now, You know that if you create a function inside the file, so if I have a function inside the file, uh, so I have a stuff.cpp over here. If I create a function over here, let me see what do I have in PRG. I don't have anything good. So in here, if I create void foo and whatever, this void foo is accessible everywhere. Void foo is accessible everywhere if I have its whole prototype. So if I actually write over here void foo, I can actually call foo in main because I have the prototype of foo over here. Are we all okay with this? Do we understand this? All right. Now, if you want this foo only to be accessible to stuff you have inside this file, so you want foo only to be of use in stuff.cpp and nowhere else. So you are writing a standalone function, you want it to be used over here. That's when you can use it anonymous namespace. You can say namespace and you do that. If you do this, then foo is only accessible here and not in other files, which means this foo that's thingy over here, as you see now, it has three wiggly thingies underneath. It means it cannot be used. It's not implemented because this anonymous namespace kind of prevents that. Do we understand this? So that's what anonymous namespaces are. If you put a name for it, obviously you can access it. You can now say stfoo. But if you don't put anything, the only place you can use the content of this namespace is this file. All right. So what do I do? What do I do? So on automatic storage, we mentioned already, it's default for local variables. They exist only during the function's execution, and when function is gone, they'll be dead, or whatever block they are in, and they are allocated in the stack. So that's what automatic variables are. They're all in the stack. Static variables, however, they last the lifetime of a program. So essentially, if I have what was I doing over here? Typedef I already did, so I don't need to change it. So if I write something like this, okay, this is a static duration, although I'm not writing static in front of it. But think about it. This is a file. So let's put it in some other file. When I'm writing this in here, this int global variable 10, it has a file scope, but its lifetime is the lifetime of the variable of the program, because when the program is actually getting executed, it will get created, initialized to 10, and the value in it will remain. Anytime I come back to the functions to this file, they can reuse the value. So global variable over here is not really global. It's file scope variable, but its visibility is only within that file and nowhere else. A static variable works the same way, but it limits the scope inside a scope. That's why writing static is a waste of characters. The two are exactly the same. It doesn't make any difference. So we put that thing out. We don't want it, but these type of variables, the global variables and the static variables, they are essentially in a static. They call it static duration of memory storage. Dynamic one, we know it's when you are creating new and delete and stuff like that. Thread storage duration, we'll talk about it. Actually, Jivan is going to talk about it. Essentially, it exists for the lifetime of a thread in which it's created. Now, you don't know what a thread is. Thread is essentially, in future, we're going to learn that you can have this function counter and you can call it 4 times that run at the same time. So we essentially do parallel processing. 4 functions will run simultaneously side by side, not one after each other. If that's the case, the variables inside those things, they coexist at the same time, but their scope is within their own thread. Each one of these execution is called a thread, and that's called thread storage, which is beyond our pay grade at the moment. We have to talk about it when in the second half of the semester, and Jivan will do it for you. Questions down to this point? All right. We talked about compilation. I did bring that image for you in class, right? With the compiler and the things, right? Yeah, okay. So we don't need to go through the compilation. Please read these things. I don't want to tell you the what happens when you put dash C dash E. Read it and please see what they are. Okay. Another thing that we need to know is this. So when you have a command line program, let me just do something in here. Okay. Copy. So let's go prompt, if I recall correctly. There you go. Okay, so this command prompt right now is where Visual Studio is creating the executable. So if I say over here, hello, and I run the program, it says hello. So if I come in here and you look at it, I have b dash may something exe, it's going to say hello. Are we okay with this, people? What did I do? Give me a thumb up or say yes. Okay, there you go. Perfect. So so I essentially am running my executable myself over here manually. Now question is that you do things like this. So I can say over here, copy b may something to hello.exe, and say one file copied. How did this information get into copy? This is an executable, right? How did these things got into copy? How could copy get these things to copy anything for me? The answer is through command line, through arguments of main. Main receives 2 arguments. Nobody uses main like this. Main receives 2 arguments. The first one is an integer. that is the count of the number of things that we have. And the second one is an array of strings. So an array of an array of strings. So I can say over here character pointer argv. So this is an array of character pointers. Essentially, each of them points to a character string. So if I write over here cout argc, see what happens now. If I just compile it like this, you will see that argc is going to say 1. And I'll tell you why it says 1. Let's come back over here. Not there. Here. Now I'm going to actually run it through this. So in here, I'm going to say b may.exe and I hit enter. My question is, how many things you see on the line? It's only 1, correct? So this is going to give you 1. Now if I say b may.exe, I don't need to put the exe. I'm going to put over here 1, 2, 3, 4, 5, 6, 7, and if I hit enter now, it's going to show 8 because 1 is this and I have 7 words. So the first one actually holds the number of things that are coming on the command line. Do we understand this? Anyone? Okay, thank you, Roman. Roman twice said yes and the rest of the people no. Anyway, so that's that. All right. The next one is essentially, because it's now say 8, we know argv0 is the first one. So I can actually do this. I can go for integer I set to 0 and I less than argc and I plus plus. In here I can actually say cout, and I'm going to actually show the thing. So I'm going to say I plus 1 and I'm going to put something like this, a column, and I put some space, and in here I'm going to say argv and I'm going to put I. So now if I run this program, you'll see that it's just going to show one thing that is actually the name of the executable. And if you see, that's how Windows Visual Studio actually call its executables, with absolute path. But if I go over here, I can simply do this. As you see, 8 of them. The first one is the name. Anything it puts over here and comes all the way down to the last one. Are we okay down to this point? Okay, so this is how you actually can receive information. There is one thing that it doesn't mention in the thing. So let me just, I'm going to say C command line arguments. There is one thing that they don't mention it in the notes that I want to tell you, and it's the third one. Now, this one is a null terminated array of strings, which means the first, it's an array, so env0, env1, env2, and each one of them is a pointer to a string. But as soon as this envx, whatever it is, it becomes null, it means it's the last one. So what I can do over here is the exact same thing, but the difference is that instead of actually checking something, I'm going to say over here envi, which means if it's not null, get in here, and then I'm going to actually show it. Now what env does is an amazing thing. It shows all the environment variables set when your application is running. So if I run this I'm going to compile it, not run it, rebuild. Now let's go here. Whoa, wrong one. So now I'm not gonna put those things anymore. I'm just gonna hit it like that. Take a look. These are all the stuff that are set in my application. All users profile is program data. Application is the user file, yada yada, roaming. My client path is that. Common argument files are these files. Program files are those. Common program Win6432 are those. My computer name is far.office. Comp specs is like what the command line that I have is command.exe. Derived data, what do I have? All the data that I have for my derived data, where they are. This is the path, the entire path that is set. These are the path. Number of it's AMD 64 is architecture. It's family 6, yada yada yada. Processor level 6. It has all the information that you want, even what is the username and things like that. So and it works the exact same way on Linux. It shows all the argument environment variables that you have that you can use in your program to decide what you want to do. Are we okay with this? All right. That's environment variables. What did I talk about? Where return statement goes to? Anyone? Oh, okay. So return statement is pretty simple. Let me just show you. Give me a second. Okay. So in here, I'm gonna put 1, 2, 3, 4, 5, something like that. So my main is not doing anything. I'm just gonna rebuild it. And come over here, clear. So obviously when I run that May thingy, nothing's gonna happen. But if I say echo $, error level $, sorry, percent sign, that's what 1, 2, 3, 4, 5 is. So the things, so in return goes to in Windows goes to error level environment and variable in Linux and obviously Mac goes to $, question mark variable accessible in bash and zsh. Do we understand this? And why do we have such a thing? So people can write shell scripts and get and see how our program ends. So we got to build a manual, and in our manual we're going to say if it returned 1, it means file couldn't open. If it returned 2, it means this. If it returned, and then they write shell script, and when they execute our program, they check the error level after. If it's 0, it means everything went good. If not, then they can add other stuff, and that's the error level. Now, uh-oh. I think something went wrong with my... Okay, it came back. Suddenly everything froze on my computer. Can you hear me? Do I have connection? Oh, okay. All right. Oh. So let's understand what constant expressions, compile time evaluation, they say. Well, let's understand what they are. So in here, I'm going to say uh, where, oh, but let me do it again. I wanted to say, uh, let's delete that. Return value of main goes to. Okay, that's that. So what are compile time evaluations? Let's focus on constant expression and static assert. So uh, the purpose of constant expression is to let variables and functions and constructors to be evaluated at compile time. Remember we talked about compile time and runtime, and we said anything that happens before the program is getting executed is compile time, and when everything is done you set the compiler aside, and now the executable comes and you run the program and it runs. Where sometimes you want certain type of evaluations to happen at compile time, so you know the values you have are legit for your program to work. So it essentially allows variables, functions, and constructors to get evaluated for performance, safety, optimization, and things like that. Okay? When they're used, when you want to, when you want the constant values that you have in your program to get computed early, like size of the arrays and things like that. Or when you want functions that are both used in compile time and runtime, you want functions that how do I explain? You want to have, say you have a value, a constant value, and that constant value you want to pass it to a function and make sure it passes certain validation. Although that function gets executed when the program is running, you can tell to the compiler, no, I want this function to actually be callable by the compiler at compile time. I know it's a little nuts, but that's essentially what it is. So yeah. So these functions you are writing should have only operations that can be evaluated at compile time. It means you cannot access the heap that is uh, the memory that the program is using during runtime, or you cannot have input output. Like for example, if I want to write, say I want to write a factorial, so int fact, it's a recursive program, and I'm going to say over here return n n less than or equal to 1, or if that's true, return 1. Otherwise, return n multiplied by factorial of n minus 1. It's a very simple recursive application. So essentially, I'm saying factorial essentially means like factorial of fact of 3 essentially is the same thing as 1 multiply by 2 multiply by 2 multiply by 3. Okay, so what does it do, this factorial? When I give 3 over here, it says is n 3? No. So call the factorial, reduce it by 1. So now it's going to go factorial of 2. Is 2 less than 1? No. So reduce it by 1. it becomes factorial of 1. So is it factorial of 1? Yes. So it's got, is it 1 or less than 1? Yes. So return 1. Now it returns 1, goes back, 1 gets returned by the 2 from the previous one, so it becomes 1 multiplied by 2, and it returns that one. It goes to the previous one, that was 3, so it becomes 2 multiplied by 3, and returns, that's the last one, so it becomes essentially 6. That's factorial. Anyways, it's a cool way of writing quick stuff. But what I'm saying is that now I can actually make this thing a constant expression, which means if I want the factorial of something to be calculated at compile time, I can create, like for example, if I want to know, if I want to have a value of factorial of 20, factorial of 20 is huge. If I want to have something like factorial of 10, actually they should have make this one long, long. That's better. So now I can actually have constant expression long f20, that is factorial of 20, equals to fact 20. Okay? Now, this f20, when the compiler is actually compiling, it will evaluate this function, run this function at compile time, not runtime, calculate the factorial of 20, put it in f20, convert that to a constant value. So this f20 becomes a hard-coded thing in your executable. It is not changeable. So you can use factorial of quad 20 in your program as a constant value. And that is called constant expression. It's embedded in your executable. It cannot change after compilation. Of course, you can use this like a regular thing in your program. So I can actually say over here, cout f20. I can do that. I can show you the value of f20, and also I can show factorial of 10. So the two values that you see over here right now when I run this program, the two values that you see over here, the first one is within your executable. It's a constant value that is not changing, but the other one is the same constant expression function that is run actually at runtime. So this is in compile time. This is compile time calculated at compile time. This one is calculated at runtime. In other words, if you actually measure the execution type of this one and this one, this will have almost zero time for execution because the value is all there, is just printing it. But this one will actually take time to run. Okay? It's as simple as that. So as you see, the other one is actually much bigger value. Oh, let me just do something else. Let me see if I do 20, how long it takes. Yeah, it's pretty quick. Yeah. Anyways, if in future I'm going to use Chrono and show you that this one is going to take longer. But anyways, that's that. So that's constant expression. And you can we have what we call a static assert. Static assert, essentially what it does is checking constant expression values to make sure they are okay and they fit certain thing, and if they don't, it's going to create a compiler. Let's put it that way. Okay? So, for example, if I am writing a program and I want to make sure that uh, when the compiler is running, the size of the an integer is 4 bytes in that system. So I can actually write static assert, and then in here I can say size of int, and I'm going to say equal to 4. Then I'm going to say in here 32-bit integer is needed for this application. Okay? And when I run this program, this is, oh, it actually ran because it's 32. I'm going to change this to 86 and see if it's going to, nah, that's going to be the same. Ta, 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 ta. Uh, what do I do? Void pointer 64-bit 8. There you go. So I'm going to say if it is, if the size of a pointer is 8, I have a 64-bit, oh, that's 64-bit, 64-bit architecture. Architecture, right? How do you spell architecture? Architecture, I think. If I'm sorry if I'm wrong. Anyways, so now let's run it. It works. Now let me change this to 886. You see, it actually shows me the error. When I compile and run it, this is what happens. No, and look at the message over here. Static assertion failed. 64-bit architecture is needed for this application. So at compile time, you can decide and find out if certain constant values, known values at compile time, actually are set. If the condition over here is true, it's going to be fine. But if it's false, it's going to create an error. Do we understand what static asserts are? Oh, Han Chen said something. Do you need to use memoization? What is this? I don't know what is memoization. What is memoization?
Yeah, so can you hear me?
Yes.
Uh, I don't know
You're talking
what's
about the are you talking about the optimization technique for
the factorial. Yeah,
oh no, forget about I cannot believe it when I'm hearing that. Good. Cool thing. Okay. So
yeah.
yeah, so what you're referring to essentially is that, but the problem is that the reason that I could do this by actually speeding up the process by creating something like this was because I knew what factorial I want.
Oh, yes.
So this speeding up the process by having previously compiled this previously compiled uh, functions only is possible if you know what the outcome is going to be. You cannot do this for runtime. Do you understand what I'm saying?
Oh, yes.
Do I am I making sense? So
Yes. Yeah.
but the one that you are saying that the technique that you are saying is can be done in runtime if functions that are complicated like this are not actually okay. Let me tell you what is the technique. You open a can of worm, my friend. So let me tell you what happens. Let's say in this factorial, I'm not talking about constant expression, regular factorial. Okay, let's say I create, I'm trying to let's say I create a static array of long longs in here. Have your and Chen, have your
Yes.
microphone on. Let's say I create a, a static array of 20 long integers in here. Got it?
Okay.
And I set all of them to -1. Every time the factorial is counted, okay, um,
Okay.
and make those, um, every time the factorial is counted, I'm going to set a couple of those things. The first one to the number of the factorial, and second one to the result it finds, and I store it in that static array. Got it?
Oh, yeah.
Then the second time the function is called, before I run the daunting task of going through factorial of 40, I'll search the
Yeah.
array and see if it's all been already been counted and calculated or not.
Yes.
If it's
Oh.
calculated, I return that one. That's memoization.
Mm,
Does that make sense?
yes.
Okay. It's not constant expression. That's a technique, a specific technique to uh, remember the values that you have calculated before, not to do it
Yeah.
over and over. Okay?
So I'm just asking, like, you're doing this fashion. Does it? I don't know whether
Oh yeah, yeah.
this
So
this way
obviously it speeds up.
is
Of
gonna
course.
take. Yeah.
Yeah.
Yes.
If I it's not for speeding up the process in this case because the number was too long and I was too lazy to type it.
Oh, okay.
That's the reason
Okay. Right
because
now.
it's yeah, okay. This is not speeding up anything. It's just you know what I mean.
Yeah.
Okay, thank you. All right. So
Okay.
sometimes every 5 years I get a question kind of wakes me up. All right. Okay, so that's that. So static assertion stuff is done. What else do we have in here to cover? Static assertion. Oh, that's it. All right. Hallelujah. We're done. So all the three things are covered. We're done. Um, uh, any questions, anyone? Anyone have any question? Activate your microphone and talk. Okay, so please don't forget to go and accept my invitations for those things. And if you are a person who were added after I populated the the let's put it this way: if you don't see the meetings in your calendar, send me a private message on Teams and tell me that I don't see my name in the calendar, and I'm gonna add you. Have yourself a beautiful day, everyone, and I'll see you on Wednesday. All right. Have a good day. Thank you very much. I really hope so too. Quite frankly, I was shouting a little too much and it hurts. Cheers. Thank you and talk to you later. Have a good day, everyone.